Welcome everyone to the sixth lecture in Mathematical Statistics in the winter term 2023-24. Before I start, I would like to ask you again, is there anyone in this lecture hall who does not speak German? Yeah, I thought so. No one raises his hand. So I have a kind of problem. What language should we use? Should we go online in English, or should we switch back to German? But of course we cannot switch the language all the time here. So I started the first few minutes in English, then we switched to German because there was no one. Then there was, for 2 lectures, there was a student speaking no German. I switched to English, and now a student is no longer there here. And I'm not sure if anyone maybe is attending this lecture only and looking at the recordings and does not speak German. But on the other hand, I don't give my lectures for people looking my recording. I give my lectures for the people who are present in the lecture hall. So what do you prefer here? Do you prefer English or German? Any preferences, or doesn't matter?
German is good.
German is good?
Yes.
Okay, and anyone who prefers English, really? Okay, well, but maybe today I give the lecture still in English, and because I will then write a Moodle message to all students and say, okay, if they want to have this language in English, then I have to show up in the lecture room. Otherwise, we will switch on Friday to German, and then it will be permanent German. Yeah? So I won't switch back. Doesn't matter who's coming. Which is a little bit of a problem, because it might be that the student is just sick, yeah, and she's missing 2 lectures, and then I'm switching the language, yeah, and this is not okay. But I don't know. It's also a disadvantage for some of you, I think. So my proposal is today I still give the lecture in English, and on Friday I ask again. And if there's and if I got an email that someone wants to come either on Friday or next week Monday, then we keep English. But if there's no one writing me an email and no one showing up on Friday, then we switch permanently to German. That would be the idea. Okay, then what did we do? Here's my slide about the last lecture. Or not the last lecture, it was a slide I've already shown in the lecture before. We have proven I've given the most difficult proof of this lecture. So from now on, everything will be more easier, which is the good news. And the proof is more or less finished. The part which is left is not difficult. It was a theorem about that there is an estimation problem which you cannot solve in some sense. Basically the distribution estimation. And the theorem says there does not exist any estimate mu and hat depending on an IID sample from a distribution mu, satisfying that the total variation distance, it's an estimate of the distribution of the sample, that the total variation distance between the estimated distribution and the true distribution, which is the supremum over all real sets B of estimated value mu and hat of B minus mu of B, absolute value of it, that goes to 0 almost surely for all distributions mu on RDBD. And here the sample is an IID sample from the distribution mu. And we did this by defining a class in a special way, defining a class of distribution on RB. So we first, I claimed that D equal 1 is enough, and then we proved it I gave a special class of distribution on R, or on the Borel sets in R, which depend on some infinite dimensional parameters consisting of 0 and 1. And what we did, basically, we started with a uniform distribution and generated a uniformly distributed random number. And then we looked at the decimal representation of this uniform distribution and used these vectors of 0 and 1 to set all these digits where the chase digit was set to 0 if the chase parameter value which we have was 0. So we modified the decimal representation. And then I've chosen this parameter purely randomly. So I choose an infinite sequence B1, B2, and so on of uniformly on the 2 points at 0 and 1 distributed random variables and use this distribution. And we showed that with the total with our estimate of this distribution, we can reconstruct a parameter. And we make a relation between the total variation distance and the error which we make with this reconstruction. And the relation was that the total variation distance is greater or equal than 0.45 times the indicator that there occurs any in predicting any of these values of the random variables, B1, B2, B3, and so on, this infinite sequence, there occurs at one point, at least at one point, an error. And then it suffices to show that this probability 1, this error occurs. And we show that this probability that an error occurs is basically the limit of capital N tending to infinity, that in the first n digits an error occurs, or in the first n parameter values. Then I derived the optimal predictor for this problem. And this optimal predictor were some random variables p and j. And if you want to, what you have given here, you have given these random digits, but you observe not these random digits, but instead you observe these random digits times the indicator that this j's parameter is 1. So either you observe this random digit or you observe 0. And from this observation, you have for each digit, you have it for, you have n, or for each parameter values you observe n such observations which are independent from all the rest. You want to predict the value bj, and the optimal predictor is just, well, that's a standard thing. We just look at the so-called a posteriori probability. You look at the probability that this random parameter bj is 1, given what you have observed. And if this probability is greater than 1/2, then you predict 1, otherwise you predict 0. So that's your optimal predictor. And what we have to show now, that this predictor, the probability of an error of this predictor in the first n digits is greater or equal 1 minus, and then 1 minus 1/2 times 1 divided by 10 to the power n, and the whole thing to the power capital N. And if you got this, as we have seen already last time, then the limit n tending to infinity will go to 1, and you are done. So that remains to show. And the problem you have here is, okay, you have this capital N unknown values b1 to bn, which are either 0 or 1, purely randomly. You don't observe them, but instead you observe random variables for each bj. You observe n random variables, and these random variables are independent and uniformly on the interval from, okay, and that's written wrong here. It's not the interval from 0 to 10, it's from interval from 0 to 9, uniform distributed random variables, times the indicator that is bj is 1. So bj is 0, that somehow it's indicated that all, if it's clear, if bj is 0, then all these values will be 0. And you can say, okay, that's rather unlikely here. Because you have n, and it could also be the value 0 if all these yij's are 0. But if you choose n uniformly on the set 0, 1 to 10 distributed random variables which are independent, then the probability that all of them are 0 is 1 divided by 10 with power n. So it's very small. And what we do now next is we actually compute this b and j bar exactly, and then we compute this probability. Okay, so let me start with the proof. Any questions so far? So we start with this. No, not this way. Proof of star. And the first thing what I want to do, we want to compute this B and J bar. And then we, to do this, I compute this a posteriori probability we have. And how do you compute such an a posteriori probability? Well, it's a conditional probability, which is basically the conditional expectation of the indicator function that this event holds. And this conditional expectation, of course, you have no idea how to compute such a thing, but you can use that this conditional probability is basically the factorized conditional probability where you plug in for these true values the random variable again. So I'm looking at the factorized conditional probability, and then the whole condition, the event that this condition holds has probability greater than 0, so the thing is basically an elementary conditional probability. And you know how to compute elementary conditional probabilities, and that's what we are doing. So we are looking at this random variable, our conditional probability, Bj is equal to 1. Given that, now I give them concrete values, Yij, times indicator function Bj equal 1, and I have to give here some real values for these, and I just give these real values in the same form. Doesn't matter, I could write some set Ij here, but I write instead small Yij times indicator of small Vj 1, and that's given for I equal 1 to n. That I want to determine. And this is now a standard elementary probability, conditional probability. Well, it's just a probability of A given B. It's the probability of A intersected with B divided by the probability of B. So you have here the probability. So it's a fraction. You have here the probability that Bj is 1 and Yij times this indicator. And that's divided by the probability of the event where we condition on. And that's what I want to compute. And I consider two different cases. And the first case which I consider, or what I would like to consider, is that one of this value which we condition on is not 0. So I consider the first case as Yij times indicator of Bj equal 1 is not 0 for some 1 less equal I less equal n. And do you have any idea what does this mean? If you have observed that one of these values where the random digit times this indicator is not 0, what does this imply? The expectation of the random digit isn't 0. No, but the expectation of the random isn't 0. But the expectation of the random variable is not equal to 0 if this is 0, yeah. Because you just observe one value, yeah. Doesn't help you. But maybe let me ask you a question. Oh, you have an idea?
Yes, we know that the product of the big Yij and the indicator function is not 0, therefore the Bj has to be 1 because else it would be 0, and therefore we know that Bj is equal to 1, and therefore both probabilities are the same.
Yes, exactly right. Okay, we know that this, for one of the I between 1 and n, this one cannot be 0. If this is not 0, then both times in the product must be unequal 0, because if one of them is 0, both are 0. Which implies in particular that this guy, so the indicator that Bj is 1, must be 1. But then this holds. And then it's clear that this conditional probability, if you condition on something which implies that the first event holds, this conditional probability is 1. And you also see it here in the formula, because if this is the case, then Bj is 1, so you can basically cancel here this Bj 1, and then you see both probabilities are the same, and the fraction is 1. So in this case, you just get 1. It's clear if you have these n random digits, which you don't observe directly, but you observe them either you observe them directly or you observe them times some indicator of something, yeah. And it's in each digit it's the same indicator, and if one of the values is not 0, yeah, then this indicator must be 1, because if the indicator is 0, then all values will be 0. Yeah? And that means that Bj. So in this case, we immediately know what Bj is. Bj must be 1. Okay? First point. The second point, we make the opposite, yeah? What happens if Yij times indicator of Bj equal 1 is 0 for all? What happens in this case? And in this case, I compute nominator and denominator separately. Okay, we know all of them must be 0. Well, due to the fact that Bj is 1 here, in this event you can basically forget about Bj equal 1 here. Yeah? I can plug in the value of, because I'm working on the event here that Bj is 1, so I can skip this here, and then Bj must be 1, and all these digits must be 0. Dj and every random variable which I have is independent. Dj takes on the value 1 with probability 1/2, and all the random digits are 0. Each one of them takes on 10 different values. One of them is 0. They are uniformly distributed on these 10 different values. So the probability that one of them is 0 is 1 divided by 10, and n of them is 0 by independence is 1 divided by 10. power n. So we are here. And now you have to compute this guy here. For this guy here, you split up the event. You insert the first the condition that bj is 0, and then the condition that bj is 1. And then you get two disjoint events, and the probability of the union and the event you have is just the union of the two. It's just the probability of those two events. The first event where bj takes on the value 0, yeah, that means the second condition is automatically satisfied because all of these are 0, and so you have only the first is only left, the bj is 0, which takes on with probability 1/2. And the second, that bj is 1, and this happens, well, that's just the denominator. So we end up with 1/2 times 1 divided by 10 is exponent n. You multiply the whole thing by 2 times 10 to the power n, and then you see the whole thing is, well, the denominator gets 1, this one gets 10 to the power n plus 1. And that's our probability. And from this you see the first probability is 1, the second one is definitely, well, if n is large, very close to 0, but even if n is just 1, it's 1 divided by 11, so it's much smaller than 1/2. So you immediately see what Bn bar is here. Because in the first case, this conditional probability is greater than 1/2, in the second case, it's less than 1/2. So we have this one, which implies J bar is either 1 if this Yij, oh no, but now I make it with capital, with random variables. Yij times indicator function which is 1 if this is not 0 for some I and 0 x. So we have the B and J, and from this we can now we know the B and J, and then I can determine my probability which I want to get. That's the Bn bars. And this vector of Bn bars is unequal to the vector of the Bj's. Or any questions up to that point? Okay. Now what we really want to compute was this probability that one bar until n bar is not equal b1 to bn. I want to compute this probability, and I compute this probability by saying, okay, that's 1 minus the probability of the complement. And the probability of the complement, that just means that they are equal, so these two vectors must be equal, so all components must be equal. And I make this as an intersection, j equal 1 to n of b and j bar is equal to bj. Next, I want to argue that these events which I have here are independent. And then I can say the probability of the intersection is just the product of the individual probability. Has anyone an idea why these events are independent?
We assume that the Yij are independent
The Yij are independent, correct?
and the Bj are independent.
And the Bj are independent?
And the random variables that we have, we can like put the Bj up to the other side if we subtract it, and then we have just a function of independent variables, and this is also independent.
We have a function of independent variables, and this independent, or I would say in this way, the event. This event, if you look at this event, on which random variables does it depend? Yeah, the chased event depends on Bj, and all random variables you use in B and J bar, but that's are the Yij. And this Yij with R as a sequence in index with I and j, they are independent from each other. So if you group them, if you group the y1j onto the ynj together, then they are independent from all other yik, where k is not equal to j. And then you see the random variables which are occurring in here are independent from all other random variables which are used in different events. So by independence you get it's 1 minus product j equal 1 to n. B and j bar is equal to bj. And I used here that this event E and j bar not equal to bj. And on which random variables it depends on, of course, bj. And then if you look in the definition of B and j bar, it's y1j and these random variables are independent from the ones which are used in the different events. Now we have to compute, oh yeah, I'm sorry. There was an error here. This is, of course, this one is a capital N. Now we have to compute these interval probabilities, and here it again turns out to be the correct way to use the compute the probability of the complement of the event. So I wrote this as 1 minus, and I don't see it myself now, but you will see in a second why this is correct. Not equal Vj. And then you see what we have to compute is basically this one, and we have to show that this is, or we will show that this is 1/2 times 1 divided by 10 to the power n, and then we are finished. And that's what I'm doing next. I look at this probability. You can basically forget about, maybe keep it. No, I forget about this one. You've already seen it. Now we compute this one, we compute the probability if B and J bar is not equal to Bj. And here I split again this event in two events. One event where Bj takes on the value 1, one where Bj takes on the value 0. And then I have a disjoint union of two events. And probability is just the sum of the two probabilities. And if Bj is 0, then B and J1 must be not equal to 0, so 1, or otherwise Bj might be 1, and B and J bar must be 0. And now, you know what the random variables are. The Bj's are independent on 0, 1. Uniform distribution 0, 1. You have this Yij, which are independent, uniform distributed on the digits from 0 to 9. And now we have to compute these probabilities. You know how B and J bar is defined? What do we get about these probabilities? Any idea? Maybe someone else this time? Someone else has an idea? So maybe look at the first one. How large is the probability, or what must be happen if Bj is 0 and B and J bar must be 1?
I think the probability of the first term must be 0.
The probability of the first term must be 0, that's correct.
Bj is 0, then there's no possibility that B and J bar can be 1.
Because if Bj is 0, then you see in the definition this Yij times the indicator that Bj is 1 can never be not equal to 0. So B and bar is 0. So the first probability is simply 0. That's fine. And the second? Well, the trick for the second is we just translate the second one, or we just plug in the definition here. So if this one, if Bj is 1, but B and J bar is 0, then this condition of B and J bar is 0 must hold. So this Yij times the indicator that Bj is 1 must be 0 for all 1 less equal E, I less equal A. And now you see, forget about the 0, first 0, I can, if Bj is 1, then here in this event, I can just forget about this indicator here, because the indicator is 1. So we have probability that Bj is 1, and at the same time Y1j must be 0 until Ynj. And any idea how big this probability is? Or what the value of this probability is?
We can split split it because of independence.
We can split it because of independence. It's a product of the single probabilities, correct?
Yes. And then the Bj has probability 1/2.
The Bj has probability 1/2 that it takes on the value 1.
And
Correct.
the Yij's have 1/10, and therefore we get
1/10. Each of the Yj's takes on each of the values from 0 to 9 with probability 1/2. So the 1/10, so the probability that it's 0, it's 1 divided by 10. So we get 1/2 times 1 divided by 10. And that what, and if we plug in this, we have the assertion. So with this one, we get the assertion. So you see, this was not difficult, basically. It was just, we know all the random variables, we just have to compute a few elementary probabilities. And of course, in the publication of this result, this whole part was not in there. Yeah? It was just mentioned that this is trivial. Yeah? No, this is true, this is true. And, but the first construction was in there. Yeah? And the first construction is the not so obvious idea. Questions so far? Then let us make a break for that I can clean the blackboard. It's now on my clock 10:27, so I will go on something like 10:30. Okay, I would like to go on with the lecture. So what we show next is that we can construct a distribution estimate mu and hat, which have the probability that the total variation distance, the supremum over b and bd of absolute value of mu and hat of b minus mu of b converge to 0 almost surely for all distributions mu on rd and rdbd and all IID random variables x1, x2 and so on, which are distributed, which has this distribution mu, in case that mu has a density with respect to the Lebesgue measure. That's our next point. So in the sequel we show there exist estimates mu and hat. And of course the estimate depends on the sample, mu and hat of x1 to xn. And goes from BD to R plus, or to R, satisfying supremum mi B and BD, mu and hat of B to 0 almost surely. We have already seen that's not possible for all distributions mu, but now we restrict the class of distribution, and in particular we restrict it such that our counter example which we had for the distribution is not contained in, and our counter example was a distribution which has, in case that our infinite vector did not only contain zeros and 1, neither discrete nor has a density, and we focus here on the case that the distribution has a density with respect to the Lebesgue measure. For all distributions, from BD of R, which have density with respect to the Lebesgue measure. And that means that you have some measurable function f such that mu of b is just the integral over b of f of x. That for all b and bd mu of b is integral over b of x to x. And of course the f must integrate to 1, but that's contained in here because I assume that mu is a distribution RDPD. And you can construct such estimates on the basis of density estimates. And the main tool to show this is the next lemma, which is the lemma of Jeffet. Lemma 3.2. Jeffet lemma says if you have densities Fg on RdBd, then the L1 distance between these densities is 2 times the integral of the positive distance between, or the positive part of f of x minus g of x equal 2 times the integral of the positive part of g of x minus f of x equal 2 times the total variation distance between f and g. So let f be g be densities on RD. That means that this measurable function don't know how to write the Vorel. Oh well, I do know. Maybe. Why is it this way? Say satisfies that I integrate to 1. And then the assertion is L1 distance between f and g, which is just the integral over Rd of absolute value of f of x, f of x minus g of x. That's 2 times integral value of f of x minus g of x. Positive part, and because of symmetry, of course, it's equal to 2 times. You can just swap f and g. It's 2 times integral of g of x minus f of x plus. And this plus part just means that you take the maximum of the argument at 0, and that 2 times the total variation distance between the measures induced by f and g. So it's 2 times the supremum over all b and bd integral f of x dx over g minus integral g of x dx integrated over zg. And I should write what the plus is. So plus is the maximum set at 0. So it's set is greater than 0 and 0. And you will prove this lemma this week in the practicing course in a formal way. What I do here is I just give a proof by picture. So it's also called visual proof or pictorial proof. I just call it maybe proof by picture. Of course, it's a very nice thing which you can easily see on a picture. So what do we need? We need two densities. And somehow I have to make a picture of a density. And then of course you know it's a function which is greater or equal to 0, and the area between the function and the x-axis must be 1. The area I can't show here in this or that it's 1 I can't show here in this picture because I don't give no labeling to the axis. But the picture you just make the standard density estimate somehow, maybe not a standard normal density estimate. So we have one density here, and that I call f. And then maybe I have another estimate, another density. Well, we have a lot of. That might be G. And now I want to find all these quantities which I have here on the picture. Maybe we start with the integral of f of x minus g of x plus dx. Where can you find it in the picture?
To the left of the intersection point is the distance of f and g, and to the right it's 0.
Okay, to the left it's the integral over the distance, so it's just the integral over this, which just gives this area here. And to the right, g is larger than f, so you integrate just 0 here. So that's basically integral of f minus g plus, marking this way. And then by symmetry you immediately see the integral over g minus f plus must be this area. And if you look at the L1 distance, what is the L1 distance? Maybe someone else this time? What's the L1 distance between f and g? So the integral over absolute value of f of x minus g of x. The sum of the two, yeah? Because it's in this area, the absolute value of f of x minus g of x is just f minus g plus, and in this area, it's just g minus f plus. And now, well, first from this one, you immediately see that this one is equal to this plus this, without the factor 2. And if we show now that the two are equal, then we have the first two equations. And the trick to show that the two are equal is you look also on the third area here, this one. And if you look now at the red area plus the white area, what can you say about this?
It's 1 by definition.
It's 1 by definition because?
Because f is the density.
Because f is density. This is the area between between f and the x-axis. So that's 1. And then, of course, same argument is g. That's the same as this one plus the right area. And then you see the red area is equal to the right area. The red area is equal to the blue area. And this implies that our L1 error, which is red plus blue, is the same as 2 times red, it's the same as 2 times blue. Same as 2 times red, and this is also the same as 2 times blue. And this proves the first 2 equality signs of the proofs. Okay? Any questions so far? And now you have to show that this is equal to this, but here instead we ignore the supremum and just look at this value without this difference, yeah? This integral over b f of x dx minus integral over b g of x dx. If you look at this, this is just the integral over some set b of f of x minus g of x. So somehow on the x-axis you mark some z b, and then you integrate f of x minus g of x in this on the set. Then you see what is the maximum value which you can get.
I would have a question to
Okay, do you have a question, please?
So we integrate. What do we integrate over? When the absolute value of f of x minus g of x.
Over RD.
Okay.
If I don't write anything on the integral, then it's always the whole the space of the measurable space. Okay. For which set do you get the maximum value here, and how large is the maximum value? If you look at the picture.
Like the x where f is bigger than g.
You integrate over all x where f is bigger than g, or greater or equal than g, yeah? Because otherwise you get something negative here. So it makes sense. So it's just this area, and then how large is it? Which area is it then?
Yeah, the red area.
The red area, yeah? On the other hand, if you want to get the lower bound, what's the lower bound? How to choose b that's as small as possible? Please?
So it's minus the blue area then?
It's minus the blue area. You just choose this area, yeah? You choose all this point where f is less than g. So it's minus the blue area. And you see the equality can be attained for proper choice of b. So the equality proper choice of b. And that's it. And in the practicing course, you will make an exact proof. And by the way, this will be one of the questions on the list of exam questions. Formulate and prove the lemma of Jeffrey, and for the proof by picture is sufficient. Or you can also give a formula. Questions? So you see, if I want, or if I use a density estimate to estimate my measure, and my measure has the density, then in case that the L1 error of my density estimate, so the difference between the estimated density and the true density, the absolute value integrated over all RD converges to 0 almost surely, then I know that this total variation distance of the measures converges to 0. And that's what we are doing next, showing that this is possible. Let's give section 3.2, which is about the kernel density estimate. And in order to motivate the kernel density estimate, I use the following lemma. Which is the density theorem of Lebesgue. So if you have a density, what is an RB? Is a density. It means that the values are greater or equal to 0 and that the integral over the density is 1. Then we have for Lebesgue almost all x, small x. And for the back almost all, I just write lambda almost all. If I take the limits of r tending to 0 of the integral over f of z dz of some small ball around, or some ball with radius r around x, and that I denote by as r from x, and divide by the back measure of the ball, then that goes to fx. Where lambda is the Lebesgue parameter, and SR of x is the ball of radius r around x. And I don't specify whether the ball is open or closed. It will be closed, but it doesn't matter. It could be open or closed. Okay, and this is very easy to prove in case that f is continuous at x. And that's what we are doing the next few minutes. And then next week in the practicing course, we will spend 1 hour, 1 hour 20 proving that you can also get it in case d equal 1 if f is not continuous. For the proof. In case that f is continuous, at x, you just look at the difference, integral over SR of x, z, divided by the Lebesgue mass measure of SR of x, minus f of x. The absolute value, and I show that this absolute value converges to 0. You replace f of x by the integral, or the f of x is the same as the integral over the constant function f of x over this ball as r of x minus the back measure of s r of x. And then you combine the two intervals. And they are here. Because just the integral over the ball is r of x of f of x dz. That's just the constant function value f of x times the back measure of the integration area, so the back measure of r of x. Then I upper bound it by using the absolute value inside the integral. And here. And you upper bound the integral by the maximum occurring value times the back measure. So that's the supremum over all z is r of x of f of z minus f of x times r of x divided by the back measure of r of x. You see this is equal to the supremum of x z minus f of x. And you see if r goes to 0, then by continuity of f at the point x, this goes to 0. In the general case, see practice. And that's it. Any questions? no questions, then I promised you to stop 16 minutes early because I lecture on Friday was a little bit too long, so I stop at this point and see you on Friday. Thank you.